Algebra of complex numbers. In this module, you will learn about algebra of complex numbers. Addition of two complex numbers. Let Z1 equal to A plus IB and Z2 equal to C plus ID be any two complex numbers. Then, the sum of two given complex numbers is obtained by adding together their real and imaginary parts. So, Z1 plus Z2 is equal to A plus C plus I within brackets B plus D. For example, if Z1 is equal to 5 plus 2i and Z2 is equal to minus 3 plus 4pi, then Z1 plus Z2 is equal to 2 plus 6i. Following are the properties of addition of complex numbers. The closure law. The sum of two complex numbers is a complex number, that is, Z1 plus Z2 is a complex number for all complex numbers Z1 and Z2. The commutative law. For any two complex numbers Z1 and Z2, Z1 plus Z2 is equal to Z2 plus Z1. The associative law. For any three complex numbers Z1, Z2 and Z3, within brackets Z1 plus Z2 plus Z3 is equal to Z1 plus within brackets Z2 plus Z3. Existence of an additive identity. There exists a complex number 0 plus I0 denoted as 0 called the additive identity or zero complex number such that for every complex number z, z plus 0 is equal to z. Existence of additive inverse. To every complex number z equal to a plus ib, we have the complex number minus a plus I minus b denoted as minus z called the additive inverse or negative of z. Difference of two complex numbers. If Z1 and Z2 are any two complex numbers, the difference Z1 minus Z2 is defined as Z1 minus Z2 is equal to Z1 plus within brackets minus Z2. For example, if Z1 is equal to 5 plus 2i and Z2 is equal to 3 minus I, then Z1 minus Z2 is equal to 5 plus 2i minus 3 minus I, which is equal to 2 plus 3i, and Z2 minus Z1 is equal to 3 minus I minus 5 plus 2i, which is equal to minus 2 minus 3i. Therefore, Z1 minus Z2 is not equal to Z2 minus Z1. Multiplication of two complex numbers. Let Z1 and Z2 be two complex numbers. Then the product Z1 into Z2 is defined as AC minus BD plus I, AD plus BC, because IB into ID is equal to I square BD, which is equal to minus BD, as I square is equal to minus 1. For example, on multiplying 2 plus 5i and 3 plus 7i is equal to minus 29 plus 29i. Following are the properties of multiplication of two complex numbers. The closure law. The product of two complex numbers is a complex number. The product Z1, Z2 is a complex number for all complex numbers Z1 and Z2. The commutative law. For any two complex numbers Z1 and Z2, Z1 into Z2 is equal to Z2 into Z1. The associative law. For any three complex numbers z1, z2 and z3 within brackets z1 into z2 into z3 is equal to z1 within brackets z2 into z3. Existence of a multiplicative identity. There exists a complex number 1 plus 0I denoted as 1 called the multiplicative identity such that z into 1 is equal to z for every complex number z. Existence of a multiplicative inverse. For every non-zero complex number, we have the complex number as a upon a square plus b square plus I minus b upon a square plus b square. This is denoted by 1 upon z or z inverse. This is called the multiplicative inverse of z such that z into 1 upon z is equal to 1, which is the multiplicative identity. The distributive law. For any three complex numbers z1, z2 and z3, z1 within brackets z2 plus z3 is equal to z1 into z2 plus z1 into z3. z3 within brackets z1 plus z2 is equal to z1 into z3 plus z2 into z3. Division of two complex numbers. If z1 and z2 are any two complex numbers where z2 is not equal to 0, then z1 over z2 is defined as z1 over z2 is equal to z1 into 1 over z2. Then on multiplying the numerator and denominator of a plus ib upon c plus id with c minus id, we get a plus ib upon c plus id is equal to a plus ib into c minus id over c plus id into c minus id. For example, if z1 is equal to 2 plus 3i and z2 is equal to minus 5 minus 4i, then z1 over z2 is equal to 2 plus 3i over minus 5 minus 4i. On multiplying the numerator and denominator with minus 5 plus 4i, we get minus 22 over 41 minus 7 over 41i. Power of I. Let us consider some positive integers as power of I. Here, I cube can be written as I square into I. This is equal to minus 1 into I, as we know that I square is equal to minus 1. So we get I cube is equal to minus I. Similarly, for I raised to 4 is equal to 1. I raised to 5 is equal to I, and I raised to 6 is equal to minus 1. Let us consider some negative integers as powers of I. Here, I inverse is equal to 1 over I into I over I. This is equal to I over minus 1. Hence, I inverse is equal to minus I. Similarly, I raised to minus 2 is equal to minus 1. I raised to minus 3 is equal to I. I raised to minus 4 is equal to 1. Therefore, for any integer k, we have I raised to 4k is equal to 1. I raised to 4k plus 1 is equal to I. I raised to 4k plus 2 is equal to minus 1. I raised to 4k plus 3 is equal to minus I. square root of a negative real number. We know that I square is equal to minus 1 and minus I square is also equal to minus 1. Therefore, square root of minus 1 is equal to I and minus I. So, I and minus I are the solutions of the equation x square plus 1 equals to 0 or x square is equal to minus 1. For example, square root 5i whole square is equal to square root 5 whole square into I square. This is further equal to 5 into minus 1, which gives minus 5. Also, minus square root 5i whole square is equal to minus square root 5 whole square into I square. This is also equal to minus 5. Therefore, square root of minus 5 is equal to square root 5i and minus square root 5i. Following are some important results. If a is a positive real number, then square root of minus a is equal to square root a into square root of minus 1. This is equal to square root of ai. Also, we know that square root a into square root b is equal to square root ab for all positive real numbers a and b. This result also holds true if a is greater than 0, b less than 0, or a is less than 0, b is greater than 0. But if a and b both are negative real numbers, then square root a into square root b is not equal to square root of ab. Identities. Following are the identities for complex numbers. Let us now prove the first identity. Here, z1 plus z2 whole square can be written as z1 plus z2 into z1 plus z2. By using distributive law and commutative law of multiplication for solving it further, we get z1 square plus 2z1 into z2 plus z2 square. Similarly, other identities can be proved. In this module, you have learnt about algebra of complex numbers.